In this video, we're going to continue looking at different types of transformations, and in this one we're going to talk about vertical and horizontal strains. So a horizontal strain about the y-axis can also be called a vertical stretch, a horizontal strain, be a horizontal stretch or compression, you might call it that, or expansion or contraction. There's a couple different words we might use for that. Okay, so if we replace x by x divided by a in the formula of relation with a constant a, positive constant a, then the graph is a horizontal strain by a factor of a. If a is positive, we have an expansion or stretch. And if a is less than 1, we have a compression. The image points are a times as far from the y-axis as the corresponding pre-image points. Let's look at a couple examples. So if we start with, say, y equals x squared, we can make a table for that. That is here. Okay. And it is the blue graph that you see here. Now, remember, as we've done before, the formula is always backwards. So it looks like we're multiplying x by 2. What we really do is divide x by 2. So notice the y is not changed, it's the x. So notice that when I'm making my tables, these are just copied over for y values so that pre-image and image will line up with the same y value. And what I do to find the image x is divide the pre-image x by 2. So negative 2 divided by 2 is negative 1. Of course, this has got to work in the formula. 2 times negative 1 is negative 2, and then square it, you get 4. So what do we do in the table? Divide the x values by 2, leave the y values alone, and we'll get image and pre-image points to line up. What does this do to the graph? Well, the y values are the same. So if we found an image and a pre-image point, like say negative 2, 4, let's see, where is that? That's negative 2, 4. That's about right here on the graph. Then its image is in here, negative 1, 4. So it's at the same height, but it's half as far from the y-axis. So horizontally we halved the distance. So we did a horizontal compression. It's like we took it on the sides and squished it in toward the y-axis. Okay. Similarly here, if we replace x by x divided by 3 in here we did it with a y equals x cubed. Y equals x cubed is the skinnier green one here. And what we did here is, again, we've left the y coordinates alone, but this time we multiply the y's by 3. See, we replace x by x divided by 3. What you really do is multiply the x values by 3, I should have said. Leave the y values alone, and so we're 3 times as far from the y-axis. The x coordinates tripled. So now it's taken and we've sort of grabbed it and stretched it out. A horizontal expansion. Okay, we can do the same thing vertically. If we replace y by y divided by b, again with the positive b, then the graph has what we call a vertical strain by a factor of b. And again, if b is bigger than 1, it's a stretch or expansion. If it's less than 1, we compress. And the image b points are b times as far from the x-axis as the corresponding pre-image. So if we have y equals x squared, that's our blue table and our blue graph here again. Okay, and we have, let's see, y over 2 equals x squared, or in other words, y equals 2x squared. Now be a little careful here. This 2 is not inside the square, so it's not properly speaking in this version either, well, with this version here, it's not quite either change of x or y, but if we rewrite it this way, we can see clearly that it's the y that's changed rather than the x. So the x is left alone for pre-image to image like this. And what we're doing with y is actually doubling it. So the y's are twice as much, 2 times as far from the x-axis, so it's twice as tall. Over here, we see y equals x cubed, and then we have 3y equals x cubed, or y equals x cubed over 3. This is 1/3 as tall, so now this one has been compressed vertically. It's gone in a third, it's only a third as tall. Now, let's talk about what we need to know here. So in general, a strain requires that we specify a line, which is the axis of the strain, and a strain factor. We move points perpendicularly toward, if C is less than 1, or away, if C is greater than 1, from the line L. So the distances of the image points from the line are C times the distances of their corresponding pre-images points from the line, and the points stay on the same side of the line. Now we're only considering strains about the x and y axis, so we have to identify the axis and then the factor. So are we moving it vertically? Are we stretching it vertically, straightening it vertically, or horizontally, and by what factor? Now notice that when you do this, when you do a single strain, you get a non-similar image. It's not only is it not congruent, it's not even similar because it modifies angles. So for example, if you started with a right angle like an absolute value function and then did a vertical strain, now your angle is maybe an acute angle or an obtuse angle. The fixed points of a strain are the points on the axis of the strain. So if you're stretching, if you're doing a vertical stretch or vertical strain, points on the y or on the x-axis are fixed. If you're doing a horizontal strain, the points on the y-axis are fixed. So not many things have symmetry with respect to a strain, but a graph with a symmetry with respect to a horizontal strain might be a horizontal line, and a vertical line has symmetry with respect to a vertical strain, but most of these will not have symmetry, so we're not going to really worry about those types of symmetries.